Hey guys, Mr. B here again, bringing you another math video. This one on finding horizontal asymptotes of rational functions. So if you don't know what a horizontal asymptote is, all it is basically is an imaginary line. So if I have a graph like this, terrible. Let's try actually use a straight line tool. So here's my set of axes. So if I have a graph, I'll just try say something that looks like 1 over x squared. So something like this. 1 over x squared looks something like this. So what you'll notice about this is that it has a vertical asymptote and a horizontal asymptote. And the horizontal asymptote is basically an imaginary line that the graph approaches as it goes to positive infinity and negative infinity. So as it approaches plus infinity and negative infinity. So as this graph, and you can imagine sort of what happens if x gets really, really big. Well, if I did 1 divided by something that's really, really, really big squared, is going to be close to 0. So as this graph gets really, really big in the positive direction, the function, or y, gets closer to 0. And the same thing goes into the negative infinity direction. As it gets closer to negative infinity, it gets closer to 0. So the asymptote in our case is actually the x-axis, so it's a line here. So usually we dot it with, if we were making a graph, we'd dot it like that. Now rational functions are unique in the sense that they always, there's basically 3 cases. This is what I'll say. There's 3 cases. There's a case where it has no horizontal asymptote, a case where the horizontal asymptote is 0, and there's a case where it's just a number. So it's not 0, it's just another number. It's moved up or down. So we'll go through those 3 cases and how you find it. But it's an important thing to remember that when you're finding a horizontal asymptote, and your professor or your teacher will probably want you to do this, is what you're actually finding is a limit as x approaches infinity, and the limit as x approaches negative infinity. Now for rational functions, it won't really matter what happens, because it's going to either approach the same asymptote or not have it. And it's only going to have one asymptote at a maximum. So if you have something a little more complicated, like a function that involves a square root, then we have to start thinking about maybe there's 2 different ones here. But we're just dealing with rational functions. It's only going to have one asymptote or no asymptotes, so 0 or 1. But that's ultimately what we want to find, is this. All right, so let's do it. So here's an example. I'm going to give you an example of where we have the highest power in the denominator. So the highest power in the bottom. So let's just come up with something. So let's say I have 3x squared plus 1. I'm going to try to make these small because I don't have a ton of room here. And let's call it x cubed plus x minus 3. So that's my rational function. Call it f of x if you want. What we want to do now, if we want to find our asymptotes, or horizontal asymptote, what we want to do is we want to take the limit as x approaches infinity. And we don't have to do negative infinity and positive infinity for rational, because we only have one, so this can do positive infinity. So the process is, what we want to do is divide by the highest power in the denominator. So the highest power, if you notice here, is x cubed. So that's the highest power. It's in the denominator. We're going to divide by that highest power. So we'll rewrite our limit as x goes to infinity, and divide every single term by x cubed. So I have 3x squared divided by x cubed plus 1 divided by x cubed. Now if you're writing this by, on loose leaf, probably look a little bit neater to mine. I'm writing it on my iPad here, so it's tough. X cubed divided by x cubed plus x divided by x cubed, and 3 divided by x cubed. So now what we want to do is try and reduce it as much as we possibly can. And I'm going to have to go up here to the right here, so don't get confused. So the limit, we got to keep it. We haven't evaluated it yet. Limit as x goes to infinity. So this guy is going to reduce the first one here. The x cubed is going to be an x squared, and then the x cubed, so I'm left with 3 over x. And then the second one doesn't reduce at all, for x cubed. all over, on the bottom I'm going to have 1 plus 1 over x squared minus 3 over x cubed. So, if you look at all these, and actually there's probably a rule I guess I could have told you, was that, and I'll just write it down here, and it's useful for this, but you don't really need to know this to understand this stuff. But anyway, the limit as x goes to infinity of 1 over x to the n, and really that 1 could be anything. It could be a 5, 10, a billion, whatever you want to have it. 1 over x to the n is always going to equal 0. So if I look, I have that situation. N could be any number besides 0. Well, it can be 1 or greater. 1, 2, 3, 4, 5. Your, I guess you'd call them your natural numbers. So if you look at this, we have that situation here with 3 over x. We have that situation here with 1 over x cubed. So those are both 0, according to my rule, once I evaluate my limit. Now 1 doesn't change. That's 0, and that's 0. So we have, everything is 0 except for the 1. So what I end up with is 0 plus 0 all over 1 plus 0 minus 0, which of course is 0 over 1, which is 0. So in this case, my horizontal asymptote is y is equal to 0. So remember, it's always a line, horizontal line, starts with y equals. So really the rule that we should take from this, and you don't have to do any of this to get it, if you have the highest power in the denominator, the asymptote is always 0. That's it. Okay? So your teacher might want you to show these workings, but in reality, if this is a multiple choice question, you don't have to do anything. Highest power is the denominator, answer is 0, automatic. Now if you look at this one, highest power in the numerator, so let's do that similar question. Let's make one up. I'll make this one even shorter. So I'll go x to the 4 plus 1 all over x to the 2 plus 3x. So again, that's my rational function with the highest power in the numerator. Let's do the limit as x approaches infinity. Divide by the I'm still dividing by the highest power in the denominator, even though the highest power is in the numerator. Some people choose the numerator. I always do the denominator. It's easy to remember. Highest power denominator, done, whatever. So let's do it. So the limit as x goes to infinity. So x to the 4 over x squared plus 1 over x squared all over x squared over x squared plus 3x over x squared. So if I look what happens, and it's pretty obvious here, I think, the limit as x goes to infinity is that I don't get 1 over something, 1 over x squared, 1 over x cubed, or whatever it might be. In this case, the first thing I get is x cubed. So if you think about it, no matter what number I'm going to put in there, if I put in 1,000, it's going to keep getting bigger and bigger as x gets bigger. It's not going to approach anything. It's just going to keep getting bigger and bigger. So, you know, for the completeness sake, I'll finish it off here. So if you look at this, this is actually infinity. This is 0, that's 1, and that's 0. So even though that's infinity, so I have infinity plus 0 over 1 plus 0, that still equals infinity. So basically what that tells me is that if the highest power is in the numerator, there's no HA, so no horizontal asymptote. So if the highest power is in the numerator, there is no horizontal asymptote. And the last case is when you have equal powers. Well, let's try one of those. So let me write out one. Let's go 3x squared plus 4x plus 1 all over negative x squared minus 4. So again, we're going to limit as x goes to infinity. Divide by the highest power, which is x squared, in the denominator, highest power in the denominator. So we have limit as x goes to infinity, 3x squared divided by x squared minus 4x divided by x squared plus 1 divided by x squared all over negative x squared all over x squared minus 4 divided by x squared. So now we start canceling. So what I notice here is my x squareds cancel. X, that's canceled. These x squareds canceled. Nothing cancels there. So I'm left with limit as x goes to infinity. So I'm left with 3 minus 4 over x plus 1 over x squared. I'll divide it by negative 2 minus 4 over x squared. And then, last but not least, we evaluate, so I'm left with 3 minus 0 plus 0 all over negative 2 minus 0. So the zeros are irrelevant. I'm left with negative 3 over 2. So again, you wouldn't even have to do any of that if it's a multiple choice question. If you look at it, if I look at my highest powers, if they're the same, you have equal highest powers. So if I look at the coefficients 3, coefficient of this guy is negative 2, so that's my answer. 3 over negative 2. So there it is. That's how you find the horizontal asymptotes of rational functions. So you got 3 cases. Highest power in the denominator, horizontal asymptote always is 0. Highest power in the numerator, no horizontal asymptote. And equal powers, that means that the horizontal asymptote is going to be non-zero. It's going to be the coefficients of the highest powers. So in our case, 3x squared, negative 2x squared, so it's 3 over negative 2. Alright guys, this was a long one. Hope this helps, and I will catch you guys later. Please subscribe, do lots of questions.